Now that we know what radians are, we're going to work a few application problems using radians. There's two important formulas that we're going to need to know, and the first one is arc length. And we've already talked about what arc length is a little bit, but let's go ahead and review that. And in this case, arc length is going to be called S. We're going to use S for arc length. And our formula that we want here is arc length then is equal to r theta, where theta must be in radians. If it's not in radians, you need to convert it to radians. So if they give you a degree measure, you need to convert it. Now arc length then, if we had a circle, I guess we don't even need the Cartesian coordinate system up here. If we have a central spot or middle of our circle, arc length would be the distance from one radius endpoint to the other. So this would be arc length. This is where theta is given, and this is our value for r. So arc length is an important formula that we're going to need to know. Our next important formula that we want to know is the area of a sector. So for the area of a sector, I'm going to call this A, and usually they use kind of a fancy script A, but I'm just going to use A for area of a sector. And A is equal to 1/2 r squared theta, and just as you might expect, this is where theta must be in radians. If it's not given to you in radians, you have to convert it. So a couple of important things here: must be in radians for both of these. And this is the area of a sector. So if we had a similar picture like we just drew up above, central point, a radius, and a radius, and we have some angle theta, the area of a sector would mean the area of this piece right here. So like if we were laying carpet in here, how much carpet, how many square yards or square feet of carpet would you need? And this angle theta is that central angle. So those are the two formulas that we're going to be using. Now that those formulas are given, I think the best thing to do is to just start running through quite a few examples. So for our first example, we'll kind of start with some basic ones. We are going to find the arc length. It says find the length to 3 significant digits of the arc of the intercepted by a central angle theta in a circle of radius r. So we could draw a picture of this. That's usually the easiest way to go. So here we have a circle, and we have some arc length, and that arc length is going to go from this point to this point, and theta is 4 pi over 3, and it's given in radians. It's very important, must be in radians. And then we also know that the radius is 14.8. So if we're asked to find arc length, the formula that we use is S equal r theta. So arc length is equal to radius. Now sometimes you will be given the arc length and asked to find the radius, and what we would do is just plug in, and then using algebra we'd solve. Now for theta, I'd plug in 4 pi over 3, and then to find my arc length, I'll go ahead and pull in my calculator and just plug it into my calculator. Now I don't have to be in radian mode here. Right now you see degree mode is flashing, and it's up here as well. I don't have to be in degree mode because I'm not finding the sine of an angle or the cosine of an angle. I'm just plugging in a radian of 4 times pi over 3. So it doesn't matter what mode I'm in, but if you're concerned, you can put it in radian mode. Second quit will get you back to your calculation screen, and I'll take 14.8. And then if you want to, you could use the fraction key, that alpha y equal, and it's the numerator over denominator, that's the n over d. And this would be 4 pi then, to make sure we get our numerators and denominators correct, over 3. And then arrow out, close parenthesis, and you can see here we get the 61.99409. Okay, so 61.99409. Now what is this? Is this degrees? Is this, what were we asked to find? Okay, so what we were asked to find then was the length of this. So this is not degrees, this is centimeters. Now our directions say to round to 1 decimal place. So rounding to 1 decimal place, that would be the 9. but the 9 following it would increase that to a 0, so this ends up rounding to 62.0. So 62.0 centimeters. So these are pretty straightforward problems. The thing you need to remember is you have to be in radian mode. Let's go ahead and look at another one. Now the last problem we looked at, it asked us to round to 1 decimal place as needed. This problem is going to be a little bit different. We're still finding arc length. They give us the picture here, so we don't need to draw a picture. But if we look at our directions right away, it says find the exact length of the arc. Now exact length doesn't mean take it out to more decimal places. It usually means leave your exact answer in terms of pi. So make sure you read the instructions here. So for this example, we'd have S equal r theta. S in this particular case is the arc length that we're looking for. The radius is equal to 5. And then the theta is the 2 pi over 5. And then we can see that the 5's cancel here, and I'm just left with the arc length is equal to 2 pi. Now if they wanted us to find a decimal, we could, but the arc length that we have, it says in terms of pi, is just 2 pi for this particular case. So again, make sure you read the instructions. Now this next one that we're going to look at, I'm still using the same formula, but instead of trying to find arc length, I'm given the arc length and I'm asked to find one of the other variables in the problem. Now our directions here, it says type an integer or a simplified fraction, so I need to remember my directions here. So the formula says find the radius of the circle in the figure at the right. Well, they give us the arc length, so the distance from here around to here is 20 pi. So start with our formula, S equal r theta. S is my arc length, so that's 20 pi equals r. R I don't know, but theta I do. It's 2 pi over 3. Now what we need to do here is recall some algebra. To solve for r, that's what I want to solve for here, I need to multiply by the reciprocal of 2 pi over 3 because I want it to cancel. So if I multiply both sides by the 3 over 2 pi, I might get some stuff to cancel here. Now on the right side, the 3's cancel, the 2 pi's cancel, and I'm left with just r on the right. Now on the left, the pi's cancel. 2 goes into 20 10 times, and 3 times 10 is 30. So here I get the radius is equal to 30. Now it says type an integer or a simplified fraction. I don't have a fraction, it's an integer value, so I can just put the value of 30 in. So even though I'm given the formula S equal R30, I could find S given R and theta, I could find R given S and theta, and I could also find theta given R and S. So that formula is really good for quite a few different types of problems. Now remember with these problems, S equal R theta, theta has to be given in radians in order to work the problem. Now if it's not given in the original problem, we can always convert anything given to us in degrees and work in radians. So for this problem, let's go ahead and draw our picture. It says how long is an arc, so S is our unknown, intercepted by the given central angle in a circle of radius 12.52 centimeters. So let's go ahead and sketch this up. So our radius is 12.52 centimeters. And then we have some arc of 150 degrees. Well, that is going to go clear over here, and that's 150 degrees. And then we're asked to find the distance from that terminal side to the initial side along the circle. So this is what I'm trying to find. So this is S. But this has to be converted to radians. So remember, 150 degrees, I'm going to write that as a fraction over 1. When I convert this to radians, I want the degrees to cancel, so 180 degrees will be on the denominator, pi will be in the numerator. Now if I look at these, 30 goes into 150 and 180. 30 goes into here 5 times, the degrees will cancel. 30 goes in 6 times here, and I'm left with 5 pi over 6. So I want to take this radian measure and put it here and get rid of the degree measure. So S equal R theta. Arc length is what I'm looking for. Radius is 12.52. Theta in this case is 5 pi over 6. Now let's go ahead and look at our directions. Round to the nearest hundredth. So this means I need to plug it into my calculator, and then round it. So I don't leave this in an exact mode in terms of pi. So I'd have 12.52 times 5 times pi, and again, if you wanted to put in your fraction key, you could, divided by 6. So here I get S equals 32.7, repeating, we'll say, 777, and it had some other things, but if I round to the nearest hundredth, which is right here, I'd look to the next place past and it would round that up, and I would get S equal 32.78 centimeters. And that's what would go here, that 32.78. Now the centimeters is already given for us, so I don't need to write that again. Let's go ahead and look at another problem. In this one we're going to be reading the degrees north, the degrees south. We kind of did some similar problems to this in a previous section. And this all has to do with arc length, so a nice picture would be helpful here. Okay, it says two cities have nearly the same north-south line of 93 degrees west. The latitude of the first city is 27 degrees north, and the latitude of the second city is 38 degrees north. Approximate the distance between the cities if the average radius of the Earth is 6,400 kilometers. So radius is 6,400 kilometers. That's important. Okay, so let's go ahead and draw this up. This would be our globe, our flat globe here. And here's the equator. And now these are both north. 27 degrees north, 38 degrees north. So that means I'm above the equator in this particular case. Now it says the same north-south line of 93 degrees west. Well, the north-south line in 93 degrees west would be somewhere over on this side, because this is the west side of the globe. So what we could do here then is we could look at this and say the first city is 27 degrees north. So we could say, okay, here's the center of the Earth. Here's 27 degrees north. Now this other one is 38 degrees north. So what I'm looking for here then is the distance between these two cities on this arc. Well, again, this angle theta has to be in terms of radians. Theta must be in radians. So when I'm calculating what's going on here, if I want to know that central angle will be the difference between 38 degrees and 27 degrees. So theta in this case would be 11 degrees. So I need to convert that. Now 11 degrees, I want the degrees to go away. So 180 degrees is on the bottom, pi is on the top, and I'm going to have to calculate this one exactly with some decimals using our calculator here. So this would be 11 times pi divided by 180. And this is going to leave me with my radian measure. So I don't want to round this. I want to make sure I keep it out as much as I can. Oh, the calculator disappeared. So 0.191986. 191986. 2177. Okay, so that's theta. Okay, so now I can just go ahead and plug it into my formula. S is equal to r theta. So this arc length S is this distance in red. Radius of the Earth, the average radius of the Earth is 6,400 kilometers. And then I multiply that times theta. And I don't want to round unless it has asked me to make intermediate rounding calculations. So I take this value that I already have in my calculator and I'd multiply that times 6,400. And I get 1228.7117. So I get my arc length is equal to 1228.711793. Now it says round to the nearest integer. So the nearest integer would be this ones position, so I'd go one place past, it's 5 or above, so this would round up. So I get arc length is equal to 1229 kilometers. So this would be 1229 kilometers right here. So a picture will be really helpful. Now this 93 degrees west is a little bit of a red herring. That is just basically providing some extra information about the north-south line. So I kind of exaggerated this as an arc, but if you had 2 points that were really close together like these 2 points, they're almost a straight line. And so that's what this is showing us, is that line that would be vertical. But again, it's a red herring. We don't need it to calculate this. Let's go ahead and look at another neat problem. I like these problems. They're fun. Some of them are some unknowns where we have to find something that we haven't been given directly. And so those are always a little bit more interesting. And for this one, it's similar to the problem that we were just working on, but we're given a little bit different information and we're asked to find something a little bit different. Okay, so I'll show you what the difference is. So for this one, it says there are 2 cities that are 1,500 kilometers apart. Well, that's already different because that's what we found on our previous problem. We found the arc length. They are giving us the arc length. So this is the arc length. And of course, S is equal to the arc length. And they tell us the latitude of the northernmost city. And they say that they're on the same north-south line, and that's all that matters right here. It says, what is the latitude of the other city? So if we come back up here and compare this to the problem that I just worked, it says the northernmost city. In our problem we just worked, the northernmost city was the 38 degrees, and they're asking us to find this other city. They're asking us to find the degrees north of the other city. And it says the radius of the Earth is approximately 6,400 kilometers. So that's important. So radius, 6,400 kilometers. So if we think about this, this is our setup. And it just says the same north-south line. So what I'm going to do is I'm just going to make a couple up. The northernmost one is 26 degrees. And then we have some other one. I don't know exactly where it is. And they tell us that this arc length right here is 1,500 kilometers. And the radius is 6,400 kilometers. And what we don't know is theta. So that's kind of the setup that we have here. Okay, so let's start with S equal R theta. We know S. S was given to us as 1,500. We know R. R was given us as 6,400. What we don't know right now is this theta. Okay, so if we solve for theta, we get theta equals 1,500 over 6,400. And again, that's just dividing both sides through by 6,400. So if we reduce this, I get theta equals 15 divided by 64. So let's go ahead and pop the calculator in. So we have, whoops, better move that up a little. 15 divided by 64. So I get 0.234375. 0.234375. 234375. Now remember, this is in radians. Theta always has to be in radians. So our problem is given in terms of degrees. So what I need to do is I need to convert this to degrees. So I'm going to take the 0.234375 radians, and I'm just going to put the radians in there. You don't have to do that. I want to be left with degrees, so degrees will go on top, pi will go on the bottom. So I'll take my calculator that I already have the 0.2343 in there, and I'll multiply times pi, or sorry, multiply times 180, and divide that by pi. And so I get the 13.42869. I'll write that down. So I get theta equals 13.42869. 42869.832 degrees. So that's this value right here. So we'll say it's about 13 degrees. Well, if this is 13 degrees, difference between the lower degree and the upper degree, this is 26 degrees. So to get this value right here, I would take 26 degrees minus 13 degrees, and I would get 13 degrees north, and that's what would go here. So we kind of have to back solve there. So that's really a fun problem. The next one that we're going to look at has to do with some gears. Let's see. Yeah, we have time. So I want to make sure I do plenty of examples because some of these examples can get a little bit hard. So let's look at one with gears in it. Okay, I'm trying to make sure that I get the picture in because the picture with these is going to be important. Now the snip on this one is going to be a little bit strange. So it's going to come in a little bit wonky. Here we are. Okay, so we have two gears here, and you can see we have the smaller gear and the larger gear. Okay, so it says two gears are adjusted so that the smaller gear drives the larger one. So this green gear drives the purple gear. It says that the smaller gear rotates through an angle of 300 degrees. Through how many degrees will the larger gear rotate? Well, what we know here is the arc length then for the smaller gear. So let's start with what we know. So arc length for the smaller gear. Now remember, arc length is given by S equal R theta. So S is our unknown. R is the radius, and we can see that the radius is equal to 3.9 centimeters. And then theta is 300 degrees. But remember, I cannot use 300 degrees. I have to convert it. I want the degrees to cancel, so 180 degrees goes on the bottom, pi goes on the top. And when I plug this into my calculator then, I will get, if I can find the calculator over here, I will get 3.9 times 300 times pi divided by 180. So my arc length is 20.42035. So let's write that down. So 20.42035. Now what we want to be careful of here is, again, theta has to be in terms of radians. So we have to convert this to radians. And I just want to point out what we did here. So remember, theta always has to be converted to radians. Okay, next. Now our whole problem was the larger gear rotates through approximately how many degrees? Well, that means for the larger gear we have an unknown angle. So for the larger gear, and that's going to be theta for the larger gear. Now if you notice in the instructions, they ask for this in degrees. So this is degrees. It says do not round until the final answer, then round to the nearest integer. And I need to make sure I convert to degrees. So again, we start with S equal R theta, and let's figure out what we have here. Well, from our picture, we know that R for the larger gear is 7.3. Theta is what we're trying to find, so S must be given as well. Well, S is the work that we did right up here. So for S, the amount of arc length, or the amount of movement on the smaller gear, matches the amount of movement along the arc right here for the larger gear. So that value is given by 20.42035,225, because again it says do not round until the final answer. So if we want to solve for theta, then I would divide both sides through by 7.3, because whatever you do to one side you do to the other. So here I get theta equals, and again we want to grab the calculator. I already have this value in the calculator, the 20.42035, etc. So I'll take that and divide it by 7.3. So I get 2.7973. 2.7973 0.8527. Now this is in terms of radians. Now remember, my answer was in terms of degrees up here, so I need to convert this. 2.797308.527 radians. I'm going to put that over 1. We want radians to cancel, so pi, and it'd be left with 180 degrees on top. So again, we're going to pull our calculator in, and we're going to take this times 180 and then divide it by pi. So this is my answer, 160.2739 degrees. So I would get 160.2739726. Now it said round to the nearest integer, so theta then would equal 160 degrees. Because the nearest integer would be the 0, this 2 does not increase that. It's not 5 or above to make that a 1, so I'd leave it at 160 degrees. So again, depending on what information is given to you, these problems are really fun to work on because sometimes you're finding something different than just the straightforward arc length. The next one I want to look at next, we'll do one more with arc length, and then we'll get into some area of the sectors. That was the other formula that we were given. This one has to do with bicycles. So let's go ahead and pull in the problem, and then we'll read through it and try and figure out how we can solve it. And they do give us a bit of a diagram to start on here. So let's kind of read through this and then concentrate a little bit on this diagram. Okay, so the figure shows the chain drive of a bicycle. Okay, so here's the pedal over here, and then this goes to the wheel. This is like the this chain is connecting the pedals to the wheel, and so we have some big wheel out here on this part. It'd be more centered, of course. Now, how far will the bicycle move if the pedals are rotated through 180 degrees? So the pedals are rotated through 180 degrees over here. And assume the radius of the bicycle wheel is 13.8 inches. The radius of the gear is 1.22 inches, but the radius of the bicycle wheel is 13.8 inches. So we kind of have a lot of information here. The only thing that we can start with is the pedal gear, because it's the only thing that we know with the radius and the theta. Now in this case, theta is 180 degrees, and that's equal to pi. And if we have to convert that, remember 180 degrees, I'd multiply by pi over 180 to get the degrees to cancel. So 180 degrees is equal to pi. So let's go ahead and think about this. I'm going to write out some information. I'm going to call this the pedal gear. So I'm going to call this the pedal gear. So the pedal gear will turn, and as it turns, it'll turn the wheel gear. And it's going to turn the wheel gear through some arc length. And I'm going to say it's unknown at this point. We're going to figure it out. So it's going to rotate it through some unknown arc. And the bicycle wheel will move through the same arc as the wheel gear. So let's go ahead and identify some things here. So this piece right here, we're going to call the wheel gear. And this big blue piece right here is called the wheel. So think about that like it had an inner tube on it. Okay, so that's kind of our first big piece of information. So our first step is to work with this pedal gear. And for the pedal gear, remember, we're still using S equal R theta. We don't know the arc length, but we know R up here is 4.62 inches. Theta was 180 degrees, or pi. So for this particular case, I'd take 4.62 times pi. Let's grab that calculator again. So I'd have 4.62 times pi. And I think it'll probably be a good idea if we don't round anything till the very end. So here I get 14.51415. 51415,806. Okay, so that's good to know. So that's the arc length for the pedal gear. And I guess if we wanted to, we could put inches on that. Okay, so our next step, the wheel gear, and we already talked about the wheel gear, that's in orange up here. So this wheel gear. So the wheel gear moves through the same arc length as the pedal gear, because it's pulled by the same chain, the same distance. Okay, so that's going to kind of be our step 2. So we're going to be working with the wheel gear this time. So again, S equal R theta. Now what we know here then, the wheel gear moves through the same arc length as the pedal gear. So that means we're going to pull this number from up here for our arc length, 14.51415,806 equals R. R, if we come up here, is this radius, 1.22 inches for the wheel gear. And of course theta then. Now solving for theta, I divide both sides by 1.22. Okay, so I still have this number on my calculator, so I'm going to divide it by 1.22. So this 11.89685,087, that's my value for theta. That's how much rotation of that central angle. So this is 11.89685,087. Okay, so that's the next piece of information I've learned. Now, what this is saying is the wheel gear rotates through 11.89685,087 radians. Okay, so another piece of information. Now we need to take this and transfer it to the wheel. So the wheel, and the wheel is what I have up here in blue, so this wheel right here. The wheel will also rotate through the same number of radians. So this would be the 11.89685,087 radians. Okay, so this would be step 3 then. We start with S equal, okay, this is the wheel, not the wheel gear. So S equal R theta. So S in this case, I'm trying to figure out, is the arc length. R is the radius of the wheel, and that is given to us as 13.8. Now this value of theta is given to us as well from step 2. So 11.89685,087. Again, I don't want to round until I get to my final answer. Okay, so grabbing the calculator, I'm going to take that number times 13.8 and I get 164.176. So S is equal to 164.17654. Now, answer up here says to round to the nearest tenth. So the nearest tenth would be this spot right here. And then I look at this 7, and the 7 is 5 or above, so that would increase that to a 2. So S, the arc length, the amount that's going to travel on the wheel, would be 164.2 inches. Okay, so that's kind of a neat problem. There are several steps to it to try and combine all of those different thoughts, but it's pretty interesting how they work out. Let's go ahead and look at one where we're looking at the area of a sector. I know we're spending a lot of time, and some of these problems are long. They might take us 10 or 15 minutes, but I want to make sure when we work through them that you have kind of some good problems to go after or to follow through when you do your own problems in my math lab. Okay, so this one, let's go ahead and get to the area of a sector. So we're not doing arc length necessarily. Sometimes arc length might pop up, but this one says the area of a sector. So the area of a sector was A equals 1/2 r squared times theta. Now remember, theta must be in radians, has to be in radians. Okay, so they just want to go ahead and find the area. So 1/2, A equal 1/2 r squared, so r squared, so that would be 7 squared times theta. I don't know what theta is, it's not given to me. So, this value of 3 pi right here, if I look from here, I'm going to put this in red, if I go from here to here, this 3 pi is arc length. And that's equal to S. Now remember, the formula for arc length is S equal R theta. So they're telling me that the arc length is 3 pi. I already know the radius is 7, so I should be able to find theta from here. So I kind of had to take a little bit of a detour, but theta equals 3 pi over 7. And then I can come and plug that in right here. Now, answers, type in exact answers in terms of pi. So that is some good direction. So A equals 1/2 7 squared times 3 pi over 7. So 1/2, 7 squared is 49 times 3 pi over 7. So 7 goes into 49 7 times. 7 times 3 is 21. So I'm left with 21 pi over 2, and that's my answer. Rounding to the nearest pi. Use integers or fractions. So 21 pi over 2. I want to make sure that my circle doesn't cover the 2. So that's the area of the sector. So that would be this right here, like if I were to carpet or tile that. So that's the area of a sector. So for this one, I did need to use arc length as an intermediate calculation to find theta, and then once I found theta, I could work from there. So again, this is similar in the fact that just because it's a formula for area of a sector, I could be given the area of a sector and then asked to find some other values from the formula. Now most of the problems that we worked on will give you a kind of some good insight on how to set up the other problems. I didn't do one of every problem that you'll see because the lecture would end up probably being like 2 hours. But everything that we looked at with those two formulas and the different procedures for stepping through them should be able to be applied to all the problems in this section. As usual, if you have questions, please let me know. You can just send me a screenshot of the problem and a screenshot of your work, and I should be able to help you out. Good luck.